In this example, we are looking at the abrasivity of clay slurries. And more specifically, we're looking at a specific problem in the brick production industry, where components are used in the processing equipment and they are suffering from quite severe abrasive wear by the clay that they are mixing and molding. And the challenge that this industry has is they have no consistent information about the wear resistance of different surface treatments or different alloys. So to address this problem, we are starting from an ASTM method. So we take our inspiration from an existing method, which is the ASTM G75. It's a slurry, sand slurry resistance test. And in this test, we are taking blocks of a material that we want to investigate. And these blocks are put in a moving arm, moving back and forth in a bath with a slurry. And the slurry creates an abrasive wear mechanism. After a number of time intervals, we are measuring the weight losses, and from these weight losses, we can distill what is called a SAR number, the slurry abrasivity response number. And the bottom line is that the lower the SAR number is, the more wear resistant your material is. This is what a test looks like in the case of sand slurry. So in the standard ASTM, a mixture is made with ASTM sand, and we are moving in this slurry. But to get closer to the industrial practice, we have modified the method and we have worked out a way to produce a consistent clay slurry. And you see that the clay slurry appears to be a bit finer. The test results show that when we are using a reference material, which is a hard tungsten carbide, in the standard methodology with the abrasive sand, we get a relatively high SAR number. With the clay slurry, we get a lower number. What's important is that these results are still fairly repeatable, just as they are with the sand. So we have a repeatable measurement method to look at the wear resistance of different materials in this clay slurry. Also important, of course, is that the wear mechanism that we are observing is the same as the mechanism that occurs in reality. And we can see in this clay slurry a mild abrasive wear process, which does correspond with the industrial practice. Now, we did a very large matrix of materials thanks to a European project that we were involved with, the PROCETS project, that gave us access to a lot of different surface treatments. And in this graph, you see the evolution throughout the project. We have defined a reference material, which is the tungsten carbide, and a reference coating, which is a currently available hard chrome coating. And the SAR numbers in the clay slurry are around 50 or below that. And throughout the project, we have looked at this green family of coatings, which are thermal sprayed coatings, and this orange family of coatings, which are electrodeposited coatings. And then you can see that when we started with a non-optimized sprayed coating, the results were not very good, but as these coatings got optimized throughout the project, we reached similar results as with the reference material. This was not the case, however, with the electrodeposited coatings. Despite a lot of optimization steps, as we get further and further in the project, the coatings actually didn't get better, and we could never reach the same performance with electrodeposited coatings as we could with thermal spray coatings. The blue and the red were coatings that we were able to also acquire during this project. These were so-called promising coatings, but a very simple and effective screening test like this slurry test shows that this red family, PVD coatings, are certainly not wear resistant enough, and that the blue family here, which are laser cladded coatings, are also not good enough to replace the current reference materials.